Hello and welcome to my YouTube channel, Training Made Clear. Today we're going to be doing a lesson on basic electricity and we'll be doing part 2A. Part 2 is actually quite big, so I've divided it into an A and a B series. Part 1, basic electricity. If you haven't seen this video, these are the topics that we discussed and went through. So please make sure you have seen the video on part 1 before doing part 2. In part 2, the effects of electricity, power and generation, you'll see the first part, the first half is 2A and the second half is 2B. In the very first video we did on basic electricity, we discussed the river of electricity. This diagram helps you to understand the basics of how electricity works and what all these different pictures mean. Introduction. Electrical effects, simple explanation. What this unit is about. This unit explains the effect of electric current, how electrical power and energy are used, how electric power is generated. All electrical machines and devices work because of the effects of electric current. Examples: light bulbs produce light. Heaters produce heat. Motors produce movement. When a device is operating, it is using electrical energy. Energy and electricity. A very important rule in science is energy cannot be created or destroyed. It can only be changed into another form of energy. Electrical devices change electrical energy into other types of energy. Some examples are the green ones are the electrical devices and the blue ones are the energy produced. So like a light bulb produces light, a heater produces heat, a motor produces movement, and a speaker produces sound. What electricity is. Electricity can be described as the effects caused by moving charged particles, usually electrons. Inside wires, tiny particles called electrons move. When they move together, they create an electric current. Static electricity is electricity at rest. Electric charges can sometimes stay in one place. This is called static electricity. Figure 1 and 2. Example you may have seen. On a cold, dry day, comb your hair with a plastic comb. Your hair may stand up or be attracted to the comb. This happens because electrons move from the hair to the comb, creating an electric charge. Objects with opposite charges attract each other. Electric current. Electricity in motion. Figures 3, 4, and 5. When electrons flow continuously through a wire, this is called electric current. You'll see the red arrow shows conventional current, which is positive to negative, and the blue one is the direction of electron flow, which is negative to positive. The flow of electrical current is shown in this figure, where you can see it going through a lamp. For electricity to flow, you need a power source, battery or generator, a closed circuit, and a lamp, a load. A motor, a heater, the flowing electrons deliver the energy to the device. See figure 4. Here you can see in figure 5 the direction of electron flow is negative to positive. You have learned that electric current is the flow of electrons. Electrons are so small they cannot be seen. Therefore, electricity cannot be seen. This is one of the things that makes electricity dangerous. However, the effects of an electric current can be easily seen. There are many things in your home or car which use the effects of an electric current. Effects of electric current. Figure 4. When a light is switched on, the effects of an electric current can be easily seen. When an electric kettle is used to boil water, the effects of an electric current can be seen. There are many more devices which show the effects of electric current. All electrical devices and equipment operate by using the effects of an electric current. Electric current has 3 effects: magnetic effect, heating effect, and chemical effect. Magnetic effect. When current flows through a conductor, a magnetic field builds up around the conductor. By placing a compass next to the circuit conductor which is carrying the current, you can see this effect. Figure 6 shows a compass next to a circuit conductor which is not carrying current. The circuit is open or off. Therefore, there is no current flow and the compass points north. When the circuit is closed or on, the current flows through the conductor and the compass needle is attracted to the wire. Here you can see the current in the wire and the compass needle is attracted to the wire. The magnetic field produced by the current flowing through the circuit attracts the needle. This magnetic effect on the electric current is shown in figure 7. The magnetic effect is important because motors, generators, transformers, lifting magnets, etc. depend on it for their operation. Heating effect. Heat is generated when current flows through a conductor. The current produces the heat as it tries to overcome the resistance of the circuit. There are many electrical devices which use the heating effect of a current. Example, water heaters, electric cookers, electric irons, filament lamps, etc. Here you can see a picture of a kettle with an electric element, and you can see a fish tank heater. Both the water heater and the kettle, shown in figure 8, use the heating effect of an electric current for their operation. Here you can see a light bulb with an electric filament. The filament lamp in figure 9 uses the heating effect of the filament to produce light. Chemical effect. When current passes through a chemical solution, it can cause basic chemical changes to take place. This is the chemical effect of an electric current. Examples of the chemical effect are battery charging, electroplating, and electrolysis. When a car battery cannot produce enough power to start the car, it can be electrically recharged. The normal process is reversed, and the current is fed into the battery by a battery charger. This is one example of the chemical effect of an electric current. Electroplating is another process which uses the chemical effect of an electric current. The meaning of electroplating is the covering of a metal object with a thin coat of another metal. Many things we use in the home or at work are electroplated. The objects are often coated with expensive metals such as gold, silver, chrome, or copper. Electrical power. When a voltage source drives a current through a resistance, some of its heat is produced. Heating effect. This is because electrical energy is being changed into heat energy. The rate at which the change takes place is called power. Power is the rate at which energy is used. The symbol for electric power is P. The unit of electric power is the watt. The symbol for the watt is W. When an EMF of 1 volt causes a current of 1 ampere to flow, the power is 1 watt. Therefore, power is equal to EMF times current, or power is equal to voltage times current. In symbols, P is equal to V times I, where P is the power in watts, and V is the voltage in volts, and I is the current in amperes. Power is the rate at which energy is used or consumed. The watt is a small unit of electrical power. When large amounts of power are consumed, then the units kilowatt and megawatt are used. 1 kilowatt equals 1,000 watts. The symbol for a kilowatt is kW. 1 megawatt equals 1 million watts. The symbol for megawatt is MW. Here you can see a circuit with a 20 volt supply and a 1 ampere current flowing through a lamp producing heat and light. Example 1. Calculate the power used by an electric lamp which takes a current of 1 amp from a source of 20 volt DC. P is equal to V times I. which is 20 volt times 1 amp. Therefore, P is equal to 20 watts. Figure 11, showing an electrical current circuit. P is equal to 20 watts. The power dissipated by the lamp is 20 watts. When something is dissipated, it is spread out in different directions. This is the case. The power dissipates from the lamp in all directions as light and heat. P is equal to V times I. Therefore, power is directly proportional to the voltage and current. The power formula P equals V times I can be transposed for V and I. Example 2. An electric kettle is rated at 2 kilowatts. When a voltage of 100 volt is applied, what is its resistance? Use the power formula to find I. I is equal to P over V. Therefore, 2 kilowatts is equal to 2000 watts. Therefore, I is equal to 2000 watts over 100 volts. I will then be 20 amps. Now use Ohm's law to find R. R is equal to V over I. R is equal to 100 volts over 20 amps. Therefore, R is equal to 5 ohms. The resistance of the heating element of the kettle is 5 ohms. The watt is so small of an electrical power. When large values of power are dissipated, then the units kilowatt and megawatt are used. The symbol for kilowatt is kW. 1 kilowatt equals 1000 watts. The symbol for megawatt is MW. 1 megawatt equals 1 million watts. Electrical energy. When work is done, energy is used. Electrical energy is the product of electrical power and time. If you use electrical power for a short time, you only use a little electrical energy. If you use electrical power for a long time, then you use more electrical energy. The basic unit of electrical energy is the joule. Energy equals power times time. E equals P times T. The symbol for energy is E. Time is T. Therefore, where energy equals energy in joules, and P is equal to power in watts, time is T in seconds, energy equals power times time. Therefore, E is equal to P times T. Therefore, where E is equal to energy in joules, P is power in watts, T is time in seconds, or where P is replaced by V times I, a joule is the amount of energy used when 1 watt of power is consumed for a time of 1 second. 1 joule equals 1 watt times 1 second. E is equal to V times I times T. Example number 1. If an electric kettle rated at 2 kilowatts is switched on for 60 seconds, how much energy is used? Energy is equal to power times time. E is equal to P times T. Therefore, E is equal to 2000 watts times 60 seconds. E is equal to 120,000 joules. The joule is a very small unit of energy. This can be seen from the example where 120,000 joules of energy is used in 1 minute. The practical unit of energy is the kilowatt hour. The joule is 1 watt times 1 second. There are 3,600,000 joules in 1 kilowatt hour. There are 1,000 watts in 1 kilowatt and 3,600 seconds in 1 hour, 60 times 60. Therefore, 1 kilowatt hour is equal to 1,000 times 60 times 60, which gives you 3,600,000 joules. The symbol for kilowatt hour is kWh. The symbol for joule is J. The kilowatt hour kWh is the practical unit of electrical energy. This is the unit by which electricity is sold. The electricity you use at home is measured in kilowatt hours. All users or consumers of electrical energy have an energy meter fitted to their building. They are charged on the number of units, kilowatt hours of energy they use. Figure 12 shows an energy meter which measures how much electrical energy is used by a consumer. You can see that thing that looks like an arrow in the middle is a disk which spins. 1 full revolution of the disk will cause the counter to step on by 1 unit. One full revolution causes the next counter to step on by 1 unit. Example 2. Calculate the energy used in joules and kilowatts when an electric kettle of 3 kilowatts is operated for 4 minutes. Step 1. Measured in joules. Change kilowatts to watts and minutes to seconds. 3 kilowatts equals 3 times 1,000 equals 3,000 watts. 4 minutes is equal to 4 times 60, which equals 240 seconds. Energy in joules, power, watts times seconds. Energy equals 3,000 watts times 240 seconds, which equals 720,000 joules. Step 2, measured in kilowatts. Change minutes to hours. 4 hours divided by 60. Therefore, energy in kilowatts equals power, kilowatts times time H. Energy equals 3 kilowatts times 4 divided by 60 hours, which equals 0.2 kilowatt hours. The energy used by the kettle when operated for 4 minutes is therefore V is equal to P over I, and I is equal to P over V. 2,000 joules or 0.2 kilowatts is what was used. Example 3. Calculate the energy used in kilowatt hours by an electric motor of 440 volts at 20 amp, which is operated for 8 hours. Step 1. Calculate the power used by the motor. Power is equal to V times I. P is equal to 440 volts times 20 amp. Power equals 8,800 watts or 8.8 kilowatts. Step 2. Calculate energy. Energy is equal to power times time. Energy equals 8,8 kilowatts times 8 hours. Energy equals 70,4 kilowatt hours. The energy used by the motor over 8 hours is 70,4 kilowatt hours. Generation. Electric power provides most of the energy people use every day. It is used in homes, schools, offices, and industries, and is available almost everywhere. Electricity is popular because it is easy to produce, sends over long distances, and it's easy to use. It has also helped industries to grow because it is reliable and fairly stable in cost. Most electricity is made in large power plants, using coal, gas, oil, or nuclear energy. However, cleaner sources like hydro, water, solar, and wind power are becoming more popular because they do not cause pollution. Electricity travels from power plants to homes and businesses through wires called transmission and distribution lines. It is always ready to use. Just turn on a switch. Electric field, law of charges. To understand electricity, we can look at what it does. For example, when you pull a comb through your hair, it can attract small pieces of paper. Another example, if you rub a glass rod with silk and touch it to a small ball of aluminium foil hanging on a thread, the ball moves away. This means that they repel each other. If you touch another foil ball with the same rod, the two balls will also repel each other. But if you rub a plastic rod with wool and bring it near the foil balls, the balls move toward it. This means that they are attracted to each other. Why does this happen? Rubbing the glass rod with silk gives it a positive charge. When it touches the foil ball, it passes this charge to them, so they all have the same charge and repel each other. Rubbing the plastic rod with the wool gives it a negative charge. When it touches the foil balls, it gives them a negative charge, so they also repel each other, but they are first attracted to the objects with a positive charge. Here you can see a drawing where figure 13, the positive and the negative are attracted to each other. You can see the middle currents pulling towards each other. This leads to the conclusion that unlike charges attract. Figure 13, unlike charges attract. Figure 14, you can see that like charges repel. The two positives are moving away from each other. This interpretation of the experiment leads to the conclusion that like charges repel. Figure 14, like charges repel. Therefore, it can be concluded that there are only two kinds of electric charge, positive and negative. Potential difference, voltage. Electric potential difference, also called voltage, tells us how much energy each charge has as it moves from one point to another in an electric field. The unit for voltage is the volt, V. 1 volt means that 1 joule of energy is transferred when 1 coulomb of energy moves between 2 points. The coulomb C is the unit of electric charge. The coulomb is the amount of charge that flows when a current of 1 ampere flows for 1 second. The formula is V equals W divided by Q. Voltage equals energy divided by charge. A 1.5 volt battery means that the positive terminal has 1.5 volts more energy per charge than the negative terminal. This difference is sometimes called EMF, electromotive force. When the battery is connected to a circuit, electrons flow from the negative terminal to the positive terminal through the wire. If the voltage is very high, electricity can move even through the air without a wire, like a spark or lightning. Electric current. Electric current is a rate of charge of motion. The moving charges may be electrons, protons, ions, or even positive holes in semiconductors. When the charge Q is measured in coulombs and the time t in seconds, the current I will be expressed in ampere, which is defined as coulombs per second. I is equal to Q divided by T. Electric circuits. When a battery is connected to an electric circuit, a current is produced. The current is directly related to the voltage, but the amount of current is also dependent on the type of conductor. Different types of conductors resist the movement of electrons with given voltage by different amounts. The resistance of a conductor is defined as the ratio of the potential difference across the conductor to the current through the conductor. R is equal to V over I. The unit of resistance is the ohm indicated by omega. The greater the potential difference across the circuit, the greater the electric current and the greater the heating effect as electrons force their way through the wire. A conductor which generates a large amount of heat is called a resistor. Resistors can be connected in series or parallel. In a series circuit, the current flows through all the resistors. The total resistance, RT, is the sum of all the resistors. If one resistor burns out, the entire circuit is broken. RT is equal to R1 plus R2 plus R3. Parallel wiring allows the electric current to move in different paths. Each branch can be switched on or off independently, allowing some or all of the devices to be used. If the resistance in one branch is increased, a smaller amount of current will flow in that branch. The more branches in parallel wiring, the lower the total resistance in the circuit, and the higher the total current. The total resistance, R1 over RT, for all resistors in parallel is given by the equation 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3. Fuses and circuit breakers. A fuse or circuit breaker can be included in a circuit to prevent overheating. If the current increases to a dangerous point, a filament in the fuse overheats, burns out, and the circuit is broken. A thick wire offers less resistance to the current than a thin wire. This is because current consists of electrons flowing through the metal of the wire. A conductor with a large cross-section allows more electrons to interact with the field. Switches. If a circuit is complete, electrons will flow as long as they are available. Usually it is desirable to be able to switch the power on and off. This can be done with switches. If the switch is open, current cannot flow. Closing the switch makes it possible for the current to flow. Circuits are opened or closed according to the position of the switch. Electrons and heat. Electron flow explains the relationship between electricity and heat. When the electric field in a circuit acts on an electron, the field gives kinetic energy to the electron. When the electron strikes an atom, it transfers most of the energy to the atom. The atom then vibrates faster. Faster vibration means more heat, since it is energy of motion. In turn, heat in metals reduces conductivity or increases resistance slightly. Increased vibration of the atom makes them get in the way of electrons more often. The electrons spend extra time on deflecting courses instead of going straight ahead. Here you can see a sodium atom. It has a nucleus with protons and neutrons, and you can see the electrons are in those orbits, and it depends on how many protons and neutrons there are in the nucleus. This one shows 11, so there will be 2 in the first circle, and then 8, and then the rest in the last circle. This is the periodic table, and these are all elements that we know of. The first element, hydrogen. You can see there's a 1 in the top left-hand corner, and then underneath it says hydrogen. The top right is the atomic weight of the atom. So you can see this one has 1 in the field, which is its atomic number, and helium is number 2, which is there on the right. And so this means that helium has got 2 electrons in the first shell. Hydrogen only has 1. So all of these on the right-hand side, where this arrow is showing up next to the Xe, these are all the atoms in their outer field where they are satisfied. And we will talk about that more later. Simplified rule for basic chemistry. There is some confusion regarding the number of electrons in a shell. Some training videos show the maximum amount of electrons in each shell is as follows. Shell 1 equals maximum 2 electrons. Shell 2, 3, and 4 each have maximum of 8 electrons. Other training videos say the following. Shell 1, 2 electrons. Shell 2, 8 electrons. Shell 3, 18 electrons. Shell 4, 32 electrons. If you look at figure 18, you can see in the first shell, maximum of 2 electrons. Then you see shell 2, 3, and 4 shows maximum of 8 electrons, called the octet state. So, which is correct? This is why we want things to be made clear in training. Actually, both are correct. The teaching of 8 electrons per shell 2, 3, and so on comes from basic chemistry teaching, figure 18, to keep things simple. So 2, 8, 8, so on. Simplified rule for basic chemistry is okay for teaching up to 20 electrons in an atom. After 20 electrons, the shells are filled differently. The 2, 8, 18, 32 actual maximum capacity used in physics is more advanced teaching, where they teach about sub-levels in energy levels. We will learn more about that 2n squared in a moment. An atom consists of a central nucleus, protons and neutrons, surrounded by electrons in energy shells. There are technically 7 main energy shells or orbitals, note it's in purple, that house the electrons. If you look at this drawing, you can see at the bottom left, there's in purple shell 1, 2, 3, and 4 written in purple. Those are the shells we are talking about. But if you look at the top right, you can see in blue, simplified rule for basic electricity. That is where they teach about the 2888 theory. But the actual more advanced is the green one at the bottom right, which is the 2, 8, 18, and 32, the green ones. That is the more advanced type of teaching. So the 2 teachings are correct. To keep atomic structure simple, think of an atom with one orbital. That atom will only be satisfied if it has 2 electrons in the first shell, like helium, because it has got 2 electrons, completing the first shell. But hydrogen only has 1 electron in the first shell. Therefore, hydrogen is unsatisfied. See figures 19 and 22, the blue electrons. From shell 2, or 3 or 4, an atom is considered satisfied or stable and non-reactive when the outermost shell, the orbital, the valence shell, is completely filled with 8 electrons. For the vast majority of main group elements, this means having 8 valence electrons, a configuration known as the octal rule. See figure 19 and 20 and 21, the green electrons. So the number of electrons in a shell is 2n squared, is the maximum number of electrons. If you want to find out how they calculate that, the n is the orbital number. So if it's shell number 3, which we'll see in this diagram coming up now, we will explain it more better there. All right, the more accurate rule, the advanced rule. The number of electrons in a shell is 2n squared. That is the maximum number of electrons energy or shell energy. Okay, so if you see shell number 3, if the 3 is the n, then it'll be 2 times 3 squared, which is 2 times 9, which will give you 18 electrons in shell 3. To explain this better, look at the right-hand side. Energy level, look at number 1, 2, 3. Then you see sublevels is SPD, and the number of orbitals in those sublevels, you have 1, 3, and 5. Then the electrons per subshell is 2, 6, and 10. If you add those together, you get 18. So orbital number 3 will have 18 electrons, which is what we see on the left-hand side. So there where those lightning strikes are, you can see those two 18s are comparing with one another. Figure 21 shows electrons and their shells. Now, in reality, electrons don't look like the little diagram on the right-hand side here, which is like our solar system. It looks more actually like the blue diagram that you see there, where the electrons are flowing in different orbitals. They're not in one plane, they're in different planes, not like the solar system. Okay, so figure 22 shows a calcium atom, which is atomic number is 20. So if you look at it, it'll have 20 protons and neutrons in the nucleus and 20 electrons in the orbitals. The first orbital will have 2 electrons. Then it will have 8, then it will have 8 again, and then in the last orbital will only have 2. So all the little ones there which are marked with an X are electrons that it wants to have but are missing. Looking at the table of elements, element number 1 is hydrogen. The one in the top left corner signifies it has 1 proton and 1 neutron and 1 electron in the field. See figure 23. So you can see it's shell number 1 only has 1 electron. It's not satisfied because it wants 2. Element 6, which is carbon, the 6 in the top left corner, signifies it has 6 protons, 6 neutrons, and 6 electrons in the field. Element 78, platinum. 78 is in the top left corner. It signifies it has 78 protons, 78 neutrons, and 78 electrons in the orbitals. Element number 8, which is oxygen, figure 25, it has 8 in the top left corner, which signifies it has 8 protons, 8 neutrons, 2 electrons in the first shell, and 6 electrons in the second field. The oxygen atom becomes satisfied in the second field when it combines with 2 hydrogen atoms sharing electrons and satisfying the outer orbitals of each atom. So there you can see when the hydrogen binds with the oxygen, which is H2O, which is water, then you see the sharing of electrons and the atoms become happy and the little green faces showing there. Element number 17, which is chlorine, figure 24. The 17 in the top left corner signifies it has 17 protons, 17 neutrons, and 2 electrons in the first field, 8 electrons in the second field, and 7 in the third field. It's 1 electron short of becoming satisfied. So when it combines with the hydrogen atom shares its electron with the chlorine, satisfying the chlorine, and the chlorine shares those 7 electrons with the hydrogen as they come through and satisfies the hydrogen. Heat can also generate electricity. By acting upon the joined ends of two different types of metals, the unheated end must be joined together in order to complete the circuit. Voltage can be increased by the joining of several junctions in series to make a thermopile. A pile made of antimony and bismuth with the unheated ends kept at a constant temperature can detect temperature changes of 1/100th of a millionth of a degree. This explains the use of the thermocouple or thermopiles in our industry. So here you can see a thermocouple. This is how it works. Thermocouples are made up of two wires of different metals which are fused together on one end. There you can see it, the hot junction. When this end is heated, it causes an EMF to be generated. Thermocouple types, we have different kinds. So the type J is iron and constantan. It can measure from -40 to +750 degrees, and you can see there that the millivolts that's generated is 8 to 42. Then you have type K, and you have type T, and you also have type R, which is platinum at 13% and rhodium, and it can generate 0 to 21 millivolts of power. Then you also have the type S. These are the popular thermocouples. There are many more, and these are the ones that are used to measure temperature. There are thermocouple tables which show the millivolts which are generated by each degree of temperature for the whole range. Thank you for watching this video. I hope you've learned something from it, and if you enjoyed it, then please like and also subscribe and share it with your friends. And thank you for watching. Stick around for the test. There will be a test of your knowledge now.